Chapter 13 is about radicals and radical reactions. It's a fairly small group of reactions, but pretty important. They involve homolysis of non-polar bonds to form things referred to as reactive intermediates. And those are very reactive. I think I said reactive intermediates. They are radical intermediates, which are reactive intermediates. Unlike other organic reactions, radical transformations are important in many biological and industrial processes. Oxygen gas, like we inhale, like we extract from air when we breathe. NO, that's nitric oxide, which is used in our bodies as a neurotransmitter. It's a vasodilator. It will cause blood vessels to dilate. Both of those are radicals. Many oxidation reactions with O2 involve radical intermediates. And then biological processes mediated by nitric oxide, like blood clotting and neurotransmission, may also involve radicals. A lot of useful industrial products, styrofoam and polyethylene, are made through radical processes, radical reactions. So that's what Chapter 13 is going to be about. And we'll move forward here. The introduction now. Radicals first discussed back in Chapter 6, but very briefly. If we have, I'll get this out in a minute. We've got two things here shown as A and B. Now this might be two chlorines or two bromines. And they are sharing a pair of electrons in a bond here. What we show is this arrow. You notice, you'll look closely, the arrowheads on here are only half arrowheads. They're referred to as half-headed curved arrows. Some people refer to them as fish hooks, and I think you can probably see why that would be. So what this shows is not that both of the electrons in this bond are moving to one atom or the other, but one of the two electrons goes here, the other one electron goes here. And that produces radicals. So, defined, a radical, a reactive intermediate with a single unpaired electron. Now listen carefully to that, unpaired electron. Sometimes people confuse that with a phrase that we've used a pretty good bit over the last year and a half, which is unshared pair, like a lone pair. Not the same thing. This is not a pair of electrons. It is not an unshared pair of electrons. It is an unpaired electron, a single electron. So, things that have unpaired electrons are called radicals. Sometimes they're referred to as free radicals. Once again, we use half-headed curved arrows to show one electron, one electron. Now, we talked earlier about this as being homolytic cleavage, or homolysis, or homolysis. There are two electrons between those two elements. Here they're indicated as A and B. We might, in fact, very shortly, we will see a bromine molecule. Two bromine atoms. Now you know that each bromine has 7 electrons. Let me draw this. Let me switch to the camera. All right. You know that bromine, one of them has 7 valence electrons. So I'm going to put them here. 3, 4, 5, 6, 7. And then I'll do another bromine. Do it in a different color. It will have 1, 2, 3, 4, 5, 6, 7. All right. So what are these two bromines doing? They are sharing this pair of electrons to form a covalent bond, a single covalent bond. for a sigma bond. But what we're going to do now is split this apart. And the word for splitting these apart is cleavage. And we can do it two ways. I could divide them right through there where I'm laying the pen. Now, doing that would not give me two things that are the same. Over here, I would have bromine with 8 electrons. But if those 2 electrons go with that bromine on the left, then the bromine on the right is not getting either one of those electrons. So, what we get over here is we have bromine with not its normal 7 valence electrons, but an 8th one that was taken from the other. That would be a bromide ion, an example of an anion. It would be negatively charged because of the extra electron. And then over here, we get a bromine that instead of the usual 7 valence electrons, it only has 6. It lost an electron to the other bromine. So this bromine is positively charged and would be called bromonium. So that is heterolytic cleavage. Hetero, different. I got two different things. I got a positive bromonium and a negative bromide. But to form radicals, rather than splitting this so that 2 electrons go to one element or the other, we split them evenly. We'll cut them through that way, which returns us to the 2 bromine atoms that were joined together to make the bromine molecule, which is a diatomic molecule, 2 atoms in it. So what we do to get these radicals is called homolytic cleavage. Homo, same. We get 2 of the same thing. And what we get is a bromine with 7 valence electrons, but that one is not paired up. That is an unpaired electron. So we have a bromine radical. So a bromine atom is a bromine radical. Now remember, we don't normally find bromine atoms by themselves free in nature. That's because they are a radical, and those radicals are very reactive. So 2 bromine atoms will find each other and come together to make a bromine molecule. Okay, so homolysis, homolytic cleavage. So a radical contains an atom that does not have an octet, making it reactive and unstable. Radical processes involve single electrons, so the half-headed arrows are used to show the movement of the electrons. 1 half-headed arrow is used for each electron. You can classify carbon radicals as primary, secondary, or tertiary by the number of R groups bonded to the carbon that has the unpaired electron. This is like when we did carbocations, but here instead of having a positive charge on this carbon, it has a radical. It's got a single electron. So here is a primary radical with just 1 R group on the radical carbon. Here's a secondary radical with 2 R groups on the radical carbon. And here's a tertiary radical. Radical carbons are sp2 hybridized. And so the p orbital that is above and below the plane of the 3 sp2 hybrids will be half occupied. It will just have 1 electron in it. Of course, it's free to roam around the blue area and the pink area, but there's only 1 there. Bond association energies for cleavage of carbon-hydrogen bonds are used to measure radical stability. 2 different radicals can be formed by cleavage of carbon-hydrogen bonds in propane. So if we remove a hydrogen from one of the end carbons, one of the primary carbons, said another way, if we remove a primary hydrogen and do it by homolytic cleavage to form a primary radical, the enthalpy change for that is 410 kilojoules per mole. Whereas if we remove the hydrogen, a secondary hydrogen, from the secondary carbon To produce a secondary radical, the enthalpy change is only 397 kilojoules per mole. So breaking the stronger primary carbon-hydrogen bond to form a primary radical takes more energy than breaking the weaker one. So the secondary radical is more stable because it takes less energy to form it. And since a secondary radical is more stable, well, that's what we were looking at up here. There's primary, secondary, tertiary. Secondary is more stable than the primary. The tertiary is more stable than the secondary. Sort of like with carbocations, a tertiary is more stable than a secondary is more stable than a primary. And let's see, so that gives us this. Here's a methyl radical, a primary radical, a secondary radical, a tertiary radical, and as we go across there left to right, we're seeing more and more stability. Alkyl groups are more polarizable than hydrogen, so they can donate electron density to the electron deficient carbon, and that's what makes it more stable. It's kind of similar to the analogy that I used with carbocations. If you are this carbon and you're a radical, think of that radical as a heavy load to carry. Well, you ain't got no help. It's you and three little scrawny hydrogens, and they can't help you. So you have to carry that heavy carbon radical load all by yourself. On the other hand, if we go to the other extreme, when you're surrounded by three other carbons, they can help you carry that load. Same kind of analogy as we used with trying to carry the heavy load of a positive charge with a carbocation. All right. And again, we've seen this before. The lower the bond dissociation energy, the more stable the resulting radical. Now, here's where there's a difference. Remember how carbocations would rearrange? You could do a hydride shift or a methyl shift to create a more stable situation. Radicals generally don't rearrange to make more stable radicals. And you can actually use that to distinguish between radical intermediates and carbocation intermediates. In other words, if you're looking at a reaction and you see, well, to get from this reactant to this product, this thing had to have been rearranged, well, that's a good indication that it probably worked by means of a carbocation. If it doesn't rearrange when it looks like it could have, then that means it was probably a radical intermediate. All right, a couple of these here. What kind of radical is that? There's a carbon there, there's a carbon there, so it's secondary. What kind of radical is that? It's bonded to a carbon over here, a carbon up here, and a carbon over here. That's 3, so that's tertiary. That one's also secondary. That should be pretty simple. All right, let's move on. General features of radical reactions: they form from covalent bonds by adding energy in the form of either heat or light. You can symbolize the heat with a delta above the reaction arrow, or you can put H nu. Back in Chem 111, we're talking about wave properties of light, and we saw that the energy of a wave is equal to its frequency, designated by the Greek letter nu, times Planck's constant, which is the h there. Let's see, just a quick reminder here. There's your Greek alphabet, upper and lower case. Nu looks like an N in the uppercase, and it's this bizarre, almost looks like an italicized V. But that is nu. That is the Greek equivalent of N for us. So that's a N sound. Yeah. You see, it's N. Sorry, that's something different. All right. Some radical reactions are carried out in the presence of something known as a radical initiator, which is a compound that contains an especially weak bond that will serve as a source of radicals. Peroxides, which have a general structure of ROOR, are the most commonly used radical initiators. Now, this, of course, would be an organic peroxide because we have R groups, which are hydrocarbon. But you can have a hydrogen here and a hydrogen here, and that would be hydrogen peroxide, which you should be familiar with. Heating a peroxide will readily cause the homolysis, the even splitting of the weak oxygen to oxygen bond, and you'll get two RO radicals. Note the RO dot. It shows you that it's a radical. A couple of common reactions of radicals. They'll undergo two main types. They react with sigma bonds, and they add two pi bonds. And in both cases, the purpose is to get to an octet. So if you react a radical X dot, like a bromide or a chloride, a bromine radical or a chlorine radical. When you say bromide and chloride, you refer to the anion. So if you use a halogen radical with a carbon to hydrogen bond, the radical will abstract the hydrogen. In other words, it will lure the hydrogen away. That will form HX. So that could be hydrogen chloride or hydrogen bromide. And the other electron in the carbon to hydrogen bond will stay with the carbon. So you get this. You get a new radical. So this halogen radical pulls the hydrogen away, and that creates a new radical. And of course, this new radical could be primary, secondary, or tertiary. It's most easy to form a tertiary because the tertiary is most stable. Right? The radical reaction typically seen with nonpolar carbon-hydrogen bonds in alkanes, which can't react with polar or ionic electrophiles or nucleophiles. So in other words, we can react the halogens with alkanes because they can react by a radical mechanism. You can also react a radical with a carbon-carbon double bond, and what it's going to do is add to the pi bond. So you got a pi bond in here, and there are two electrons in that pi bond. We can take one of those and put it with the one electron shown on this fishhook arrow from the halogen to create a new sigma bond right there, shown in red. But the other electron in the pi bond goes to this carbon and stays there as an unpaired electron. So we get a radical. If a radical reacts with a stable, single, or double bond, you get a new radical formed. Okay? And although the electron-rich double bond of an alkene will react with electrophiles addition mechanisms, it also reacts with radicals because they are also electron deficient or electron poor. You can have two radicals react with each other. This is related to what I was saying with two bromine atoms or two chlorine atoms. They have in their atomic state, they have that unpaired electron and they don't like it. So two radicals can come together that are alike and form a diatomic molecule. Okay? Reaction of a radical with oxygen, which is a diradical in its ground state configuration, is another example of two radicals reacting with each other. So here you can see that O2 can exist here as a diradical. A lot of times we see it drawn by pulling both of these in and forming a double bond. In this case, the reaction of O2 with the radical forms a new radical, preventing the X, the halogen radical, from reacting with an organic substrate. Compounds that prevent radical reactions are called radical inhibitors or radical scavengers. So oxygen can do this, so can vitamin E, and we'll see some more things closely related to that later in the chapter that work as radical scavengers. And also, there's another little hint, if radical scavengers prevent a particular reaction, that's a good indication that that reaction was a radical reaction. All right, what we got next? I can't see down here. Not sure what my time is. So, for some reason. All right, so I think the thing to do here, been running about 20 minutes. A good point to cut this off and move on to the next video.